Hello everybody. Today we're going to be looking at the second part of section 2 in chapter 3. Remember, we're looking at Newton's laws of motion. He came up with 3 that govern how forces affect motion. We looked at the first law of motion, the law of inertia, the other day. Now we're going to look at the second law, Newton's second law of motion. Okay, so what does it say? It says if a net force acts on an object, it will make the mass of the object accelerate. Now, up here, the first law, the net force was 0. All the forces balanced out, so the object couldn't change motion. There was nothing to change the motion. So it either stayed at rest or it stayed at constant velocity. But what if the net force is not 0? Well, that's what this law is telling us. If there is a net force, if it's not 0, if all the forces do not balance out, whatever is left will make the mass accelerate. So, how do we determine Newton's second law mathematically? Well, the acceleration is directly proportional to the net force and inversely proportional to the mass. We'll look at that in a minute. But this is the formula by which you can determine the acceleration produced by a net force. Now, I have found in the past that if people try to remember this form of the formula, they invariably accidentally write it upside down. They'll say m over f, which you cannot do, obviously. So the easiest way to remember this formula is to actually, since you're dividing by the mass on this side, you multiply it on the other side, and you get F net equals mass times acceleration. I like to look at it this way. The net force makes the mass accelerate. You're writing it in a sentence, aren't you? It's just using math symbols instead of words. The net force makes the mass accelerate. In other words, second law is Fermat. I like that. The second law is Fermat. Okay? Now, we can use this, but let's make sure that we can do the algebra correctly. So I've created a math triangle for us, and we're going to put the net force that acts on the object in the top, and we're going to put the mass here and the acceleration here. Now, how do you know what to do each time? Well, we put the multiplication right here. See? Net force, if you're looking for the net force, cover that up. You're going to take the mass and multiply by the acceleration, which is exactly what this says. You're going to take the mass and multiply by the acceleration. If you're looking for the mass, you're going to take the net force and divide by the acceleration. And if you're looking for the acceleration, you're going to take the net force and again, you're going to divide by the mass. Okay, so division's here, multiplication here. Just cover up the one that you're trying to find, and it tells you what to do with the other two. Force divided by acceleration. Force divided by mass. Or mass times acceleration. Okay, that's how we can use that triangle. And you will be using that on Friday in order to practice some problems. However, for right now, let's continue with looking at Newton's second law to see how it works. This says the acceleration is directly proportional to the net force acting on it, which is exactly what I said up here. So that means if the net force gets larger, so does the acceleration. In fact, we call this a linear relationship. And if we draw a best fit line for the points, there we go. We can see as the force value gets bigger, the acceleration value gets bigger. In other words, push harder, it goes faster. That makes sense to us, doesn't it? Okay, in fact, if you look right here, here's where we can look at a couple of examples. Let's suppose that both of these cars have the same mass, because all we want to look at right now is the force and the acceleration. So we'll keep the mass constant. Remember, in goods, 5 kilograms. Sorry about that, guys. That's supposed to say 5 kilograms. In good science, you can only change one variable at a time to see how another variable affects the one in question. So, look right here. If both of these cars have a mass of 5 kilograms, if the net force acting on one of them is 10 newtons, then to get the acceleration the car would have, then we're going to say the net force divided by the mass, that would be 10 newtons over 5 kilograms, and we get 2 meters per second squared. So there's the acceleration right there, okay? But look at this second one. Now he's deployed a parachute, sort of like some of the Formula One race cars, you know, and to help them stop in a shorter distance, they deploy a parachute. But the parachute is producing 7 newtons of drag opposite the forward force acting on the car. So that means we have to put them together to get the net, but they point opposite directions. So if we take the forward direction to be positive and the reverse direction to be negative, the net force is going to be 10 plus a negative 7, or if you will, remember adding a negative is the same as subtracting. So 10 minus 7, you get 3 newtons of net force, and it's positive. So, because this one's the bigger one. So you have 3 of this left over, and it's going to make the mass of the car accelerate, but by how much? So we're going to say the net force divided by the mass, and that's going to be 3 newtons divided by 5 kilograms, and you get a value of only 0.6 meters per second squared. So look, this acceleration is much smaller than this one because the net force is smaller. Here the net force was 10, here it was 3. So the harder you push, the greater the acceleration. The smaller the push, the smaller the acceleration. Okay? All right, now let's look at what happens if we see how mass affects the acceleration. Okay? How does mass affect the acceleration? Well, here I have 3 cars, but they're not the same mass this time. The little toy car here has only 5 kilograms of mass. This one 10, this one 15. But we have the same amount of force exerted on each one. Now think about it a minute. If you had a box and you put a couple of books in it, it wouldn't be very difficult to lift it. But if you put more books in it, it would be a little harder to lift. If you put a lot more books in it, it would be even harder to lift. You'd have to use more force. But when the force is the same and your mass is getting bigger, how does that affect the acceleration? Well, let's take a look. Over here on the graph, it sort of shows what happens. As the force gets, as the mass gets larger, for the same amount of force, the acceleration it goes through gets smaller. See, we start with a little mass and a lot of acceleration. But out here, we have a lot of mass, but only a little acceleration. And we call this a hyperbola or inverse relationship. In other words, as the mass gets bigger, the acceleration gets smaller. And as the mass gets smaller, the acceleration gets larger. Okay? So let's look at this over here now, our 3 little cars. In order to get the acceleration, we have to take a force and divide by the mass. So in this case, it's going to be 5 divided by 10. Oops, I wrote that backwards, didn't I? I feel like an idiot. I wrote it upside down, the numbers, not the formula. I wrote the numbers upside down. Hang on, guys. Let me fix this. Okay, now we've got it. All right, so force divided by mass, that's going to be 10 newtons over 5 kilograms. So that's going to be 2 meters per second squared, just like it was on the other page. So there we have 2. But now we're going to double the original mass of 5. So what's that going to do to the force? Let's take, not the force, the acceleration. Let's take a look. Force divided by mass, that's going to be 10 newtons over 10 kilograms. 10 divided by 10 is 1 meter per second squared. So notice, when we doubled the mass, we ended up with half the original acceleration. We go from 2 to 1, don't we? That's half. Now, suppose we triple the mass. Now we have 15 kilograms. That's 3 times 5. So how does that affect? Well, it's the same force of 10 newtons divided by 15 kilograms. And when you divide it out, you get, well, 0.67 meters per second squared. This is a third, okay? This is a third of that one. So that means it takes 3 times the mass, and you get 1/3 the acceleration. Twice the mass, you get half the acceleration, all right, of what you do with the original mass. Kind of wild that it works that way, doesn't it? Okay, so that's an inverse. All right, if we look at this example, just to show you how it works, we're going to go through our 3 steps. The first thing we're going to do is read the problem and identify the given information and what we're trying to find. So we have a 12,000 kilogram tractor trailer rig. It's at rest at a red light. So what's the 12,000 kilograms? That's the mass. Okay, remember, kilograms of mass. When the light turns green, the driver moves the rig forward with an acceleration of 0.8 meters per second squared. So there's the acceleration. And we want to determine how much force did the engines exert to produce that acceleration. So we want the force, F. If you go back to your triangle and to your formula, you can see Newton's second law says the force equals the mass times the acceleration. So we take the 12,000 kilogram mass and we multiply by the acceleration. And if you stick that in your calculator, and you can take a moment to do that, just pause the video, do it on your own calculator, see if you get the same answer that I'm going to get, and then check. Okay, if you did it on your calculator, you should have 9,600 newtons, 9,600 newtons. And that's the answer. It would take 9,600 newtons of braking force for this, or not braking force, of acceleration force for the rig to accelerate from rest when the light turns green. Okay, that's a lot of force. Now, the takeaway here. When you're applying Newton's second law, if all the forces do not balance out, in other words, if there's something left over when you add the forces, okay, then what's left is the net force, and it will make the mass accelerate or change motion. And that's where we get FMA. The net force will make the mass accelerate. Now, how was that for a nice little formula? It's easy to remember, isn't it? Okay, so there we are. I hope you all saw that whole statement. Let me put it right there so you guys can, can I get the whole thing on there? This is net force, net force. Okay, so there it is. You can write that down. Take your time. And thank you guys for listening today. This is one, looking at Newton's first and second laws is one of my favorite things. I love those two laws because they're fun to use, I think, and I'm going to try to help make it a little fun for you too. And tomorrow when you do your discussion, again, there's going to be one video that's going to show how Newton's second law can apply to football in the NFL. So that'll be kind of cool. All right, see you guys later. Have a good day. Bye-bye.